So let this is a resistor of resistance R. So it is a conducting medium. So definitely this can be considered as the source of thermal noise. Let this is the Boltzmann's constant, and T is the ambient temperature. In degree Kelvin. Let this G is equivalent to, so 1 by R, the conductance of the resistor that we consider. So conductance in Mohs. Let this alpha is the average number of collisions. Per second of electrons. We are letting this alpha is average number of collisions. We already know that as the electrons move or wander randomly in the crystal lattice, so they collide with the walls of the crystal and they collide with the other particles. So we are letting the average number of collisions per second of electron as alpha. Then we can define a quantity here called as 2kT G into alpha square divided by omega square plus alpha square. So this ratio is termed as the power spectral density of the thermal noise current that is flowing through this resistor of resistance R. So if you let I of T is the thermal noise current, due to the random motion of charged particles, some random current flow through the resistor. So that current is I. Then the power spectral density or the power density of that current, noise current, is SI of omega, and that is given by 2 kTg alpha square divided by omega square plus alpha square. And these are the terms in this particular equation. So this equation is first derived by Nyquist. After some experiments, thermal experiments, we come to a conclusion and derive an expression for the power spectral density of the noise current that is flowing through the that is generated in the thermally agitated resistor. So this resistor is the thermally agitated resistor. Due to the thermal agitation, the charged particles constitute some amount of current. So that current is a thermal noise current. So definitely we can evaluate the power or the power spectral density. That is how that particular current is varying. Actually it is a random current. So we can characterize using the statistical measures. So in the frequency domain, we can describe it by its power spectral density. So the power spectral density of this noise current is given by 2 kTg alpha square divided by omega square plus alpha square. Here K is constant. If you keep the temperature constant, that can also be constant. the conductance is also constant. So therefore, the power spectral density is depending on the number of collisions of the electron. The number of collisions, average number of collisions per second. How many collisions will be there? The average number of collisions will be very, very large. The order is around 10 power 14. So this indicates this is a very, very large number. Is it? So alpha is very, very large. So with this, we can write this as SI of omega is equal into 2 kTg divided by 1 plus omega by alpha plus. Is it right? Or take the alpha square outside in the denominator, alpha square get cancelled in the numerator, you get 1 plus omega by alpha also. This omega value, if you let omega is 10 power 13 radian per second. Why I have chosen 10 power 13? So this 10 power 13 radian per second include all the frequencies that are of practical importance. We take the audio frequency spectrum, audio frequency range 20 to 20 kHz, that is below 10 power 13. So RF, radio frequency range, it is also less than 10 power 13. We take the microwave frequencies, that is also less than 10 power 13. So therefore, if you let omega equivalent to 10 power 13, almost it includes all the frequencies that are of practical importance. Therefore, with these two values, what is the ratio omega by alpha? This is equivalent to 0.1. Is it right? So this is important for us. That is, we are letting the maximum frequency. Therefore, this omega by alpha for this particular 10 power 13 frequency, this omega by alpha is equivalent to 0.2. Follow? So if this omega by alpha is 0.1 for very, very high frequencies, so this 0.1 is very, very less when compared to 1. Is it? So therefore, can I write this SI of omega as 2 kT into G approximately? Because if you let this omega by alpha is very, very less, when it will be in the order of 0.1 if the frequency is very, very high. Normally in practice, the frequencies that we consider are always less than 10 power 13. The frequencies are always less than 10 power 13. So this value is always less than 0.1. So if it is always less than 0.1, when compared to 1, that is very, very less. So we can neglect that, and yes, the power spectral density of the thermal noise current can be approximated as 2 kT. 2 is constant, Boltzmann constant is constant, the T is constant, G is constant. So therefore, the power spectral density of the thermal noise current can be considered as constant. Is the TST of thermal noise current. Is constant for all practical purposes. That is the noise power spectral density. The power spectral density of the thermal noise current is given by 2 kTg divided by 1 plus omega by alpha square. So if you plot this as a function of omega by alpha, see how it looks like. This is omega by alpha is in the denominator. So if omega by alpha is increased, SI of omega value will decay. Therefore, maybe like this. So it is symmetric. So when omega equivalent to 0, what is the value? Omega by alpha is 0, so 2 kt g. And half of that value is kt into g. When omega by alpha is 1 or minus 1, this will become kt into g. So if you consider, see, if this is 1, somewhere here we have the 0.1. So when omega by alpha is 0.1, see, this can be approximately considered as constant, almost constant. Follow? If omega by alpha is very nearer to 0.1, this can be almost not varying, that can be considered as constant, this ratio. So therefore, SI of omega is equivalent to 2 kt into g when omega by alpha is less than or equivalent to 0. Now, if you consider this case, that is for omega by alpha less than 0.1, that is for all practical purposes, the power spectral density is constant. What that indicates? Constant power spectral density. That is, if you plot again, if you let this is 0.1 and this is minus 0.1, this is equivalent to 2 kt. That is, for omega by alpha less than 0.1, the power spectral density is constant. What this indicates? That is, at 0 frequency, this is a power. At some other frequency, this is a power. At some other frequency, this is a power. That is, the power is same for all frequencies. So what is the maximum frequency that we consider here? That is 10 power 13 radian per second. That is up to 10 power 13 radian per second. The power spectral density is constant. That indicates all the frequencies have the same distribution of the power. So that's why this particular thermal noise is also called as white noise. Why? Because the white indicates all the frequencies. So white color is the merge of all the colors. All the colors merged into the white. That is all the frequencies, all the wavelengths. So here also the power distribution is same for all the frequencies that are below 10 power 13 radian per second. So 10 power 13 radian per second is very high frequency. So all the frequency ranges that we consider in the practical applications are always less than 10 power 13 radian per second. So therefore, the power spectral density of the thermal noise current is constant. Here this term white comes from all the frequencies. So white includes as the merge of all the colors. Of frequencies. Understood why the thermal noise is also called as the white noise? And this is also called as the Johnson noise. J.B. Johnson, who first studied or developed the concept of the thermal noise. That's why this thermal noise is also called as Johnson noise. So Johnson noise, white noise, thermal noise, all are same. Understood this? So in the next class we see the modeling of resistor by a noiseless resistor. Here the resistor can be considered as the source of thermal noise.